In this video, we're going to take a look at what happens to these radioisotopes as they emit energy and go through this, what we call a decay process. So this graph should look familiar. This is the band of stability graph. A decay series is a series of steps by which a radioisotope that has an unstable nucleus decays into a stable nucleus. So as the radioisotope emits radiation and emits all this energy, the core of it, the nucleus, goes from being unstable to stable. So remember what makes the nucleus unstable. It is when the neutron to proton ratio is too high. So just to review, for your smaller atoms with atomic numbers less than 20, a stable nucleus is when the neutron to proton ratio is 1:1. The large atoms, the neutron to proton ratio is 1.51 to 1. So keep in mind. Now, decay series uses multiple alpha and beta decay steps to reach a stable state. Alpha decay makes the nucleus smaller by giving off 2 protons and 2 neutrons. So remember, this is equivalent to a helium-4 nucleus. It tends to happen when the nucleus is larger than 83 nucleons. So nucleons, remember, is protons and neutrons together. Okay? Beta decay changes a neutron into a proton and an electron where the electron is emitted. So it tends to happen when there are too many neutrons. So as we go through the decay series, you want to keep these steps in mind when predicting each step in the nuclear decay series. If the atomic number is greater than 83, we're going to use alpha decay, or we're going to use the alpha particle to show that it's going through alpha decay. And then if the number is at or below 83, we're going to show a beta decay. Stop as soon as the atomic number is at or below 83, and the ratio of neutrons to protons rounds to 1.51 or less. So keep your periodic table handy and keep your calculator handy. Write the decay series for radon 222. Again, keep these steps in mind. I have it in the top right corner of your screen. So these are basically the nuclear equations that we went over in the previous video. So we're going to start with radon 222. Look on the periodic table for the atomic number, and we have atomic number 86. So this here, if you take a look again at the 3 bullet points that I wrote on top right of this screen, we see that the atomic number is greater than 83, so this will go through alpha decay. And remember what an alpha decay emits. It emits an alpha particle, which is represented by the helium-4 symbol. And then in order to figure out our missing piece, what the daughter isotope is, we need to, again, do the math that we did, that we went over in the previous video, solving for the mass number and then solving for the atomic number. And through the atomic number, we can figure out our element symbol. So here we have 222 is equal to 4 plus x. X then would be 218. But now looking at the atomic number, 86 is equal to 12 plus y. Y would be 84. Use your periodic table to look at number 84, and we have the element polonium, Po. Now, this atomic number is still greater than 83, and so we're just going to continue with the decay series without even having to determine the ratio of the neutrons to the protons. So now we start with the daughter isotope that we ended with in this first nuclear equation. So we start with polonium 218. And again, because this atomic number is greater than 83, it will go through alpha decay. And again, we take the same steps to figure out the daughter isotope in this nuclear equation. So we have the mass number as 214. The atomic number is 82. 82 on the periodic table is lead. So here you need to pause at each step, and you need to ask yourself, is this number at 83? Is it greater? Is it below? Okay, so here we have 82. It's below 83. So take a look at the third bullet point on the top right of your screen. We need to pause here and figure out our neutron to proton ratio. So remember how we determined the number of neutrons for this isotope here? Okay, we take the mass number minus the atomic number because the atomic number tells us protons. So we have 132 neutrons, and that's to 82 protons. So you do want to simplify this ratio because, again, we're more interested in the ratio of 1.51 to 1. So you do need to simplify it. So you're going to go ahead and divide by 82 on both sides, and we get 1.61 to 1. So this ratio is still above 1.51 to 1. It means that the nucleus is still unstable. So from here, we just continue our decay series. So now we start with lead-214. You see that the atomic number is below 83. So here, instead of doing alpha, it will go through beta decay, 0, -1e. And to solve for this, our mass number, it will be the same, 214. Our atomic number will be 83, and element 83 is bismuth. So again, here we need to pause and calculate the neutron to proton ratio because the atomic number is at 83. And so we calculate the number of neutrons, and that's 131 to 83 protons. And the ratio for that will be simplified ratio for that will be 1.58 to 1. So again, you see that it's not at 1.51, so we have to keep going. So you can imagine some of these decay series are actually extremely long. Some of them are really short. So let's go ahead and continue with bismuth 214. It is at 83, the atomic number is at 83, so it will go through beta decay. Here is our new isotope. We call it daughter isotope. And you'll see that it is now back to polonium. But what's different about this polonium as opposed to the first daughter isotope polonium is that the mass number changed. Okay, so as it again goes through this decay series, the number of neutrons and number of protons are going to continue to change because the whole point is that this unstable nucleus is trying to get stable. So here we're not calculating the neutron to proton ratio because the atomic number is greater than 83. Remember that you only calculate the neutron to proton ratio when it is at or below atomic number 83. So we continue, and now that the atomic number is 84, it will go through alpha decay, and now we have our daughter isotope lead-210. And because of the atomic number, we want to again pause and calculate the neutron to proton ratio. So we have 128 neutrons to 82 protons, and to simplify that, we have 1.56 to 1. So we have to keep going. So now starting with lead-210, it will go through beta, and our new daughter isotope is bismuth-210. Go ahead and pause the video here and figure out your next steps. Continue the video when you are ready. So again, we stop and figure out the neutron to proton ratio. The simplified ratio is 1.53 to 1. So that tells us that we have to keep going. Bismuth-210 will go through beta decay. We're back to polonium-210. We don't need to figure out our ratio because, again, the atomic number is greater than 83. So polonium-210 will go through alpha decay. And we have lead-206. Again, we pause to figure out our neutron to proton ratio. And we are finally at 1.51 to 1. This right here is the daughter isotope, the stable daughter isotope. Each radioisotope has a half-life. The half-life is the time required for half of the atoms in any given quantity of a radioactive isotope to decay. So for example, let's take a look at strontium-90. Strontium-90 has a half-life of 29 years. That means that if right now you have 10 grams of strontium-90, 29 years from now, that 10 grams is going to get cut in half. Or it's going to decay, and now you only have half remaining. So from 10, in 29 years, you'll have 5 grams of strontium-90 remaining. 29 years after that, you'll have half of the 5, which is 2.5 grams. 29 years after that, you'll have half of that, which is 1.25 grams, and so on and so on and so on. If we're looking at the percents, we begin with 100%. 29 years later, we have 50%. 29 years after that, half of 50 is 25%. 29 years after that, half of 25 is 12.5%, and so on and so on and so on. The question for you is, will this ever reach zero? And the answer is no. It will get pretty close to zero, but it will never reach zero, meaning that there will always be very small traces of radioisotopes left on this earth. And that's one of the reasons why so many people are concerned with nuclear power plants, because of all the waste that comes from nuclear power plants. So the waste goes into the water or into the air, and then think about where it goes after that. It's in our water source, it's in our soil, then it's in our plants. The animals eat the plants, and we eat meat, and so then now it goes to us. And so that's the main concern with radioactive waste, that it never truly goes away, that there's always small traces that are left behind. Here's another way to look at it. So as you can tell, we are going to be doing some math. There is a formula you could use. Amount remaining is equal to the initial amount times 1/2 raised to the total time over the half-life. Some of you guys who love formulas will use this. You will see that throughout the video I will not be using this. I am going to use a timeline, a number timeline, similar to what you see here, like this table here, because I think it's a little bit easier to understand and see what's going on with the half-life and radioisotope. So let's take a look at example number 1. The half-life of thorium-227 is 18.72 days. How many days are required for 75% of a given amount to decay? You will see that with every half-life problem, these 4 variables are mentioned. We have the initial amount, final amount, half-life, and total time. And so it does help to write down these 4 things, these 4 variables. And so for initial amount, we have 100%, because this problem is talking about percents. Final amount, so how much remains after 75% is decayed? 25% remains. The half-life is 18.72 days, and the question is asking for the total amount of time. So I'm going to use the number line that I talked about a few minutes ago. And the way that the number line works is that you have your initial amount on the left side of your paper and the final amount on the right side of your paper. We begin with 100%, and as it decays and goes through a half-life, okay, we represent that with an arrow. So in 18.72 days, 100% of this radioisotope decays, and now we have 50% remaining. Now we have to get to our final amount of 25% that remains, so half of 50 is 25. This took another 18.72 days, which means that it's a total of 37.44 days. So it took thorium-227 37.44 days to decay to 25%. So let's take a look at example 2. The half-life of iron-59 is 44.5 days. How much of a 2-gram sample will remain after 133.5 days? So again, we want to figure out these 4 pieces of information. For short, on your paper, you can write IA, FA, HL, and TT. So we have the half-life. We have the time passed, the total time. And we have the initial amount, 2 grams. And it wants to know the final amount. So we're going to use the number line again. So again, initial starts over on the left. Final starts over on the right. We have 2 grams that we're starting with. And when it goes through 1 half-life and it decays to 1 gram, right, half of 2 is 1, this took a total of 44.5 days. And we want to go until it says 133.5 days. So we keep going. Half of 1 is 0.5. This took another 44.5 days, but that is a total of 89.0 days. So we keep going. And half of 0.5 is 0.25, and that took another 44.5 days, which means a total of 133.5 days. So our final answer is 0.250 grams. Now, notice that I did consider significant digits. Whether you are using the formula or doing it the number timeline way, you're still doing math, right? And what we're doing here is we're just multiplying and dividing. And so we do need to look for the least amount of significant digits. If you're looking at all of your numbers, the least amount of significant digits is 3. And so that's why my final answer is 0.250 grams. So if you, just to recap, what we're doing on top of the number line is that each time we are dividing by 2. On the bottom, what we're doing is we're adding by the half-life as it goes through each half-life, which is represented by the arrows. Let's take a look at another example. Gallium has a half-life of 68.3 minutes. We have an initial amount of 16 milligrams. And it's saying that it goes through 2 half-lives. How much is left over? So it doesn't specifically give you the total time. However, it does say that it's going through 2 half-lives. And that's what the total time over the half-life would give you. It gives you 2 half-lives. So we begin on the left with 16 milligrams. And after it goes through 1 half-life, half of 16 is 8. So we have 8 milligrams after 1 half-life. After the second half-life, half of 8 is 4 milligrams. And that right there is our final answer. Next example, the half-life is 7.04 years for uranium-235. It took a total time of 28.2 years, or that's how much time has passed. 12.5 grams remains. What was the initial amount? So here, we're actually going to do things backwards. We're going to begin with our final amount at 12.5 grams, and we're going to work our way up to our original amount. So first, to make our lives easier, let's go ahead and figure out how many half-lives this went through. So 28.2 years divided by 7.04 years, we have 4 half-lives. So that makes it easy for us because when we draw the arrows, we know that we just have to draw 4 arrows. So if we're working backwards, here's the first half-life and first arrow. Now we're not dividing by 2, but instead we're going to go ahead and multiply by 2. So we have 25.0 grams. After the second one, we have 50 grams. After the third one, we have 100 grams. And one more, we have 200 grams as our final answer. This problem is asking for the half-life. You have the initial amount of 100 grams, final amount of 12.5. Total time that has passed is 21 seconds. So if they give you the initial amount and the final amount, go ahead and make the number line. So half of 100 is 50, half of 50 is 25, and half of 25 is 12.5 grams. And I know these are easy numbers, and we've been doing 100 a lot as our initial amount, but that's just because this is practice and it's quick and easy. So this is saying that from here to here, it took a total of 21.6 seconds. Well, I want to know just one of these half-lives. So how do I figure that out? 21.6 divided by 3 is correct. So we have 7.20 seconds as our half-life. Copper-66 undergoes decay of 51 minutes. The half-life of copper-66 is 5.10 minutes. Determine the approximate factor of copper-66 that remains. So this is actually asking for a fraction. What is the fraction that remains? So here, what we're going to do is we're going to go ahead and calculate the total half-lives that it went through. Okay, so here's what the symbols are using the formula from the very beginning of this video. It really just means total time over the half-life. That's what we've been doing in these previous problems. So we have 51 minutes total time divided by the half-life, which is 5.10 minutes. So that's a total of 10 half-lives that copper-66 just went through. So in order to find the fraction that remains, all you have to do is this here. And again, this is taken from the formula. This is really the only part we need to know from that formula. 1/2 to the nth power, and again, n stands for the total time over half-life, which is really the 10 half-lives. So we have 1/2 to the 10th power. So this comes out to 1/1024. So this much of the radioactive sample remains. Let's take a look at this graph and use this to determine the half-life and other pieces of information that the problem could be asking for. So this one says determine the half-life using this graph. So what you see here is the percent remaining on the y-axis and the time on the x-axis. And notice that this is the initial amount. So that right now is 100% as the initial. And it's still the same concept. So when 50% remains, we take that over to the graph and see where that hits. And that, we bring it down. And that is 10 minutes for the half-life. Well, what if the problem asks you how much time did it take for 25% when 25% remains? So you would go to 25, where it hits the point on the graph, go down, and that would be 20 minutes. Now, I could also ask you how much remains after 30 minutes. So then in that case, you would look at the time first, 30 minutes, go up to the graph, hit the curve, and this time you read the y-axis. And so that would be right around 13% remaining, right? How much time did it take for 70% to remain? So that would be right around maybe 8 minutes, 7 minutes. And that's it for half-life.